This is Knowledge Engineering with Semantic Web Technologies, and this is one of the extra parts of Lecture 4, OWL Rules and Reasoning. In the last part, or in the last extra part of the lecture, we have talked about the simple interpretation of single triples or a graph, but we have not taken care of the meaning of RDF and RDFS. So also for that we need an interpretation function. So let's recall the simple interpretation treat all URIs that really occur within the triples the same. They do not take care whether they stem from the RDF or the RDFS vocabulary. So therefore, for understanding the RDF vocabulary, additional requirements, of course, are needed concerning the correct interpretation for simple interpretation. So therefore we define an additional interpretation, and first we start with the interpretation of the RDF vocabulary, where we have parts like RDF type, RDF property, we have RDF statement for reification and stuff like that, and also we have parts of lists here. Okay, so we have to define additional mapping functions for them. So let's have a look, what do we have to do? So we start again an RDF interpretation for RDFS vocabulary V is a simple interpretation, for the vocabulary V, and of course combined with our RDF vocabulary that additionally satisfies a set of conditions that we will state right now. First of all, okay, we say if X is element of IP, then and exactly then, of course, this is only the case if X is of type property. So X is in the extension of the property RDF type. And of course, the extension must be then a property. So subject X, property RDF type, and object property. So only then is X also really in the set of IP. So this means in the end, I have a type definition and say something is of type property. If something is of type property, then of course it must belong to P. So X is a property exactly if it is connected to the resource denoted by RDF property via the RDF type property. Okay, so now it's clear what has to be mapped to IP. So let's have a look at the literals next. So if S is an XML literal, so if this is part of our vocabulary, and S is a well-typed XML literal, then of course, if I apply the interpretation function of literals on that, the outcome is the XML value of S. And of course, the outcome is part then of all the literal values, which again, we know that is a resource. And of course, this, what I have here, is of type literal. So also you must have again have this mapping of the extension function or in the extension function of your type. So exactly this is also the literal value, the typed XML literal is of type XML literal. So nothing more to say about that. Okay, so we have taken care about well-typed XML literals. Of course, they can also be ill-typed. Then, of course, you have a problem if it's ill-typed, because then you have to make clear, okay, then it's not, if I apply the interpretation function, it's not a valid part of our set of literal values. Okay, it's not member of that. And of course, it's also not part of the mapping function. So it's not an XML literal because it's ill-typed. So this means, okay, we have wrongly typed, or we have some clashes, XML clashes in our RDF, and then of course exactly this will hold. So we talk about properties, we talk about well-typed literals, XML literals, and ill-typed XML literals. What else? In addition, there are so-called axiomatic triples, and these triples must be true. Therefore, they are so-called axioms, which means that we define that RDF type is of type property. So this is a property. We say subject is a property, predicate is a property, and also RDF object is a property. So these are parts of RDF statement, which is for reification. Then as part of lists, we say the first element in a list, so RDF first, this is also a property. We say RDF rest This is also a property. And RDF value, we haven't talked about that. This is also something to denote. So this really is only a property without further specifying any semantics. And it can be used, for example, to define structured data. So you can look this up in the RDF definition. And then we have the parts also here for the RDF containers. We have here so RDF sub 1, sub 2, and so on and so on. And these are all properties. And then, of course, we have the end here, RDF nil, which is then also of type RDF list. So this is a list, but it's empty. Okay, so these are axiomatic triples, and they must all be true. So they hold. And together with the three conditions we had beforehand, they form the so-called RDF interpretation. And now for the entailment function, a graph G1, RDF entails another graph G2 if all RDF interpretations that are model of G1 are also model of G2. So see, RDF interpretation is rather simple because more than that for reasoning over RDF is not required. So now we have taken care about the RDF vocabulary. What's next or what's missing is the RDFS vocabulary. And also for RDFS, of course, we have to introduce another interpretation. And you see here, now it becomes a little bit more complicated because there is more semantic hidden in it. So you have, of course, domain and range, and this must be explained. And you have subclass relationships and you have subproperty relationships, and of course, they have to be somehow interpreted. So let's start with that. But to simplify the representation first, we define another function, which is the class extension function, ICX. And this maps, of course, classes and lists all the elements which belong to the class. So this is the class extension function, and we will need this class extension function later on. And then we have another set defined, which is IC, which is the class extension of RDFS class. So this is the set IC, which contains all the available classes. So IC is the extension of the special URI RDFS class. Okay, what will we do with it? So we start now and define what is an RDFS interpretation for the RDFS vocabulary V. And this is an RDF interpretation for the vocabulary V combined with the RDFS vocabulary that additionally satisfies, again, a set of conditions. So first one, let's start with that. We say everything or every resource has the type RDFS resource. So if we look in the class extension of RDFS resource, we will find all resources. That's pretty easy. So the next thing what we want to do is we want also to apply this class extension function on RDFS literal. So it means every well-typed or untyped literal has the type RDFS literal. Next thing what we want to do is we want to talk about domain and range. So if X and Y are in the extension of RDFS domain, which means X has the domain Y, and you have another triple where U and V are combined via the property X, so this is in the extension of X, then it's true that the domain of X, so U, is Y, because we have defined it here to be Y, the domain of the property X. So, and this is simply stated here with the help of some first-order logic or logical expressions. And then again, you can do the same if you define Y as being the range of your property X. Then you can say if you have a triple UXV, then of course V must be in the class extension here of the property Y, and this then is the range. So this is the class of the range, the class restriction. This is also pretty clear and simple. Next one, what we have to define, we have to look at the subproperty. and of course the extension of all subproperties. So if I apply that, subproperty is reflexive and must be transitive. So you could also write this down with the help of formal logic, but we simply do this here in natural language, and you can easily translate it then into a logical axiom. So simply to say, of course it's reflexive, of course it's also transitive. So, and the next thing we want to consider here is if X is a subproperty of Y, and then of course X and Y are properties, and also the extension then of the property X, so all the elements which are combined here are also, or are a subclass, or are a subset of all the elements which are in the extension of Y. So, of course, this means that it's a subproperty. Okay, but this, of course, is not sufficient. We have to go further. So the next point is, okay, if X is in IC, which means X is a class, then, of course, X is a subclass of resource, which means everything is a resource here. So every class is also a resource. Next, number 8, if X is the subclass of Y, then of course both are classes, X and Y are classes. And again, if I look at the class extension of both classes, then the class extension of X must be a subset of the class extension of Y. Next one, again, also subclass in the same way as subproperty, of course, is reflexive and transitive on the set of classes. Next one, container membership properties. Yeah, okay. If X is one of these container membership properties, then X is always a subproperty of RDFS member. So there are severals. So this again gives some meaning to these container membership properties. And then the next one, if X is in the extension of the data types, of RDFS data types, then it means that X always is a subclass of an RDFS literal. Okay, so far so good. And then there are some additional axiomatic triples, which first of all, you can read them, then I will not read it to you because they are too many. They, for example, define for the properties that we have first, what are the domain of these properties? First, only as an example, so type, of course, has the domain resource. This is quite easy. Or domain has the domain property. This is very interesting. Or range also has the domain property because it maps a property to a class. So you should look at them. This is domain definition. Then the next part is range definition of all of these properties that are available here. And then there are additional some special vocabulary parts like the container membership properties, which is a subclass of property. And then you have these types of containers, alt, back, and sequential. And they are also subclasses of container, and so on and so on. So there are many things or many axiomatic triples that in addition must hold to define the meaning of an RDFS interpretation. And in the end, of course, you can say if all this holds and if you have a graph G1, this graph G1 RDFS entails another graph G2 if and only if all RDFS interpretations that are a model of G1 are also a model of G2. Only then you have an RDFS entailment, which is valid. So now we have defined simple entailment, RDF entailment, and RDFS entailment. The problem is, if you consider all these interpretations that we see here, and if you want to define a computer algorithm which computes RDF and RDFS interpretations according to the specifications I have given you, this is often not really efficient. And simply because of that, one uses so-called abbreviations, which is a deduction calculus. And about that, we will talk in the next extra part of the lecture.